Okay, so we've got 10 vector space properties. We've already dealt with 3 of them. I think it was closure under addition, closure under scalar multiplication, and the distributivity of scalar multiplication, which are kind of the 3 biggies that tend to mess things up. The inverse property also does. We might have dealt with that one. These are fairly familiar. And certainly the one we're going to start with to answer this question, which is closure under addition, it's usually the first thing we check. Okay? Because it's the one that fails most often. Another one being inverses. And distributivity can fail. Okay? So, using these 3 properties, and there are 10 properties, they're listed on page 191. This is numbers 1, 6, and 7. Okay? 4 and 5 are existence of 0 and inverses. They're also biggies. Most of the others are pretty obvious. Okay? And those are actually fairly obvious in most cases. Okay. Well, one that isn't totally obvious is closure. Okay, but it always has to be checked. Okay, so singular 2x2 matrices is a space of all singular 2x2 matrices a vector space. Okay? So we start by proving one property at a time. So we focus on one property. I recommend we start focusing with closure kind of as a default, but if you see another one that's vulnerable after you get a little experience, by all means, go after it. If you can disprove any property, then you don't have to do anything else. You've shown it's not a vector space. It's not interesting to us. Okay? Okay, so space of all singular 2x2 matrices. Well, prove or disprove that the sum of 2 non-singular 2x2 matrices is a non-singular 2x2 matrix. Okay? Now, I don't know what you would go about trying to do to prove this, but often we want to start off by trying to disprove something. Okay? Because something isn't a vector space, there's often an easy way to disprove closure. Okay? Or to disprove one of the other properties if closure happens to work. Okay? So, first of all, of course, we want to say, well, if I add a couple of 2x2 matrices, I do get a 2x2 matrix. So I want to focus on the non-singular part. Okay? So, an example with an eye to disproof. Okay? Give me an example of a 2x2 matrix that's not singular, that's singular. And it's singular, not non-singular. Okay. We usually write. I use the word non-singular a lot more than singular, and you pretty much do in linear algebra. So sometimes my hand writes it, and my brain lets me do that. Okay, sorry. Singular. Okay?
2, 1, 4, 2.
Give me a non-singular matrix. If we want to get 2 non-singular matrices, we start by getting one of them.
Okay. All right. So you want a non-singular. Or a
Did I say non-singular?
Yeah.
Give me a singular matrix.
2, 1, 4, 2.
2, 1, 4, 2. Okay.
Well,
I would have chosen something simpler, but that's okay. Too simple, that's good. Okay, give me another one.
Let's see, 1122.
Well, if I add those, I get 3, 2, 6, 4. Nice. Still singular, right? Can you find something I could add to this one that would give me something that's not singular? You got a little too much of a pattern in this one. I would have chosen something that didn't have quite as clear a pattern. Okay, in choosing the matrix, I choose something. Whoops. And we're talking about singular matrices. I choose a matrix with a lot of zeros in it, but not all zeros. Because of course, if I add the zero matrix to this, I get the same thing that's still singular. Okay?
Okay.
As my intuition tells me, then my intuition's not always on track. But that was what you had, right? Maybe one of the simplest things to do would be add this to 1, 0, 0, 0. Okay? Because that's really simple, and we can, by trying something that simple, we can see if simple is good for our purpose, which is to try to disprove this so we don't have to write out a bunch of symbols and prove it. Okay?
Okay.
Well, of course, you know, that messes it all up. That changes this, but none of the other none of the other terms. Okay? So, statement. These are both singular. Okay? What we done. Okay?
Okay.
And the way I would play around with this is I'd go ahead and start with any, that's perfectly okay. Not singular matrix, okay? I mean, 1, 1, 0, 0 would be a perfectly good one too, right?
Mm-hmm.
Okay? And then if I add, what would I do to this matrix to make it singular? Well, if I change any one of these numbers, it'll be non-singular, right? Okay, I said make it singular. Take this singular matrix and make it non-singular. Change any one of these numbers. How would I change any one of these numbers? Just pick which number I wanted to change and add the matrix that changes it. Okay? So eventually, you start seeing such things. Okay? And I would have started with a simpler matrix, but this was simple enough. I'd have started with 1, 1, 0, 0 and say, well, if I add 0, 0, 0, 1, now I've got two numbers in the diagonal and 0 in the other diagonal, so I get a non-zero determinant. Okay? Okay, so that's the idea. That's a proof by counterexample. Okay?